Let's quickly recap what we studied so far. We started from a very simple toy problem where we tried to build a line separating our positive examples from our negative examples. To do that, we collected a training data set with the coordinates of each of our points and also the label that said 0 if it's a negative example and 1 if it was a positive example. Then we created model parameters, model weights, which get multiplied by each corresponding coordinate plus a bias term that we add at the end, and we add all of those components together. Then we compute the value of this function, and from that we are able to compute the loss, which loss indicates how incorrect our model prediction is. And then we use calculus to compute the derivative and get the gradient. And we perform a tiny step in the direction opposite to the gradient to make our model slightly less incorrect than it was before. And we repeat this step many times until the model is good at separating negative and positive data. Then we saw that the same technique can be extrapolated to many dimensions. And we perform the same operation where we perform this operation that is called the dot product. Each corresponding element gets multiplied by its corresponding weight, and then the whole thing gets summed up, and we also add the bias term. We saw a piece of code that performs this in PyTorch, and then we saw that we can stack things together to create a batch of training data, so that in one single step we can process multiple training examples. Each of them gets separately multiplied, the dot product multiplication, with our weight matrix, which gives us a separate result for each of the input samples. From that, we can compute one loss, which is a sum of all the losses. And that loss will give us a gradient to update those weights, which is roughly an average of what it would be if we did each of these training samples individually. And that helps us optimize our training such that a lot of operations are happening in parallel in our GPUs, and we can train a lot faster. Okay, now we want to switch to a new problem. This is an MNIST dataset which was released about 30 years ago, if I'm not mistaken. And the dataset contains handwritten digits. So each training sample is a 28 by 28 image, 28 by 28 pixels. Which are represented, each pixel is represented by a number between 0 and 1, where 0 means like it's a completely dark point, and 1 means it's like the brightest point. And each image comes with a label. So this one is label 5, which means that the handwritten digit is 5 here. We have a held out dataset, which means that the dataset itself has about 100,000 training samples, and we take some of those and set it aside for validation later. So we will not train on those training samples that we set aside, such that we cannot cheat. We cannot train our model on those training datasets, on those held out samples, and we will only use them to validate our model after we trained it. So how we will train this model to recognize digits? There are many ways of doing it. There are a lot of research has been done how to train this, but we will use the simplest thing. We will just use what we learned so far, which will not be state of the art. It will not be the best model possible. First thing we will do is that we will flatten our images. So instead of having a 28 by 28 two-dimensional image, we'll just flatten it into one long vector of 784 numbers. So imagine we take the first row of this image, all these numbers between 0 and 1 that indicate how bright or dark it is. And then the second row, we just concatenate it to our vector, and then the next row and the next row, all 28 of them. Altogether, it gives us 784 numbers. Now, it might sound silly, and it is silly. By doing it, we're losing the two-dimensional structure of the image. Our model no longer knows that this pixel was above this pixel, that there is some proximity in two-dimensional space between pixels. Now it's just like one long vector of numbers, and the model does not know where each of the pixels was initially. So we will not be able to achieve state-of-the-art results, but it's still, you will see that we can still get about 90% accuracy. So it means that for 90% of our held out samples that we held out, it will give a correct answer anyways. So it's not a bad model. Okay, so how we do it? How do we do what we did before with these vectors? So let's see, we have a vector of 784 numbers, right? Let's say that for now we want to just build one model that recognizes just the digit 3. So that's just digit 3. We don't care about recognizing digit 4 or 5 or 7, just digit 3. So we know how to do this. We already built a system, as we saw here, that can take an input vector of arbitrary length and a label that is 0 or 1, and it can build a model that recognizes that that can separate the negative from positive examples. So there is only one change that we need to do to our data set. We changed the label in our dataset such that if the label was digit 3, we create a new label 1, which means it's a positive example, and any other label, which label 6 or 7 or 2 or 8, will say it's 0, which means it's a negative sample. So we'll still use this whole dataset with all 10 digits that we have, but only digit 3 will serve as a positive example, and all other digits will serve as a negative example in our dataset. And with that, we can use exactly the procedure that we listed here, and we will build a recognizing ML model for digit 3. And then we can build another model to recognize another digit, digit 6 or digit 1 or digit 7. So we can build 10 of them, and we'll have 10 different recognizers. Each will have its own weights and its own biases, right? So for each of these models we have, because the input is 784 numbers, right? That's our input, a vector of 784 inputs. It means that the weight of the model also has 784 weights and one bias, right? So that's for each of the digits. Now we will have 10 of those. But we don't want to train we don't want to train 10 separate models. We can use a nice trick that is allowed by linear algebra. We will actually train all 10 together. So we'll create a matrix where all weights for the digit 0, they go in column 0, like in the first column. All weights for the digit 1, so this would be the model that recognizes digit 0. This would be the model that recognizes digit 1. This would be the model that recognizes digit 2, and so forth. And we just stack them together, all 10 of them. And this image is actually misleading because each column here is 784 elements, but it's only 10 elements wide. So it's actually a very, very tall matrix. And then the biases, again, we have 10 biases for each of this recognizer, right? For each digit, we have its own bias. So the bias term becomes now a vector. Previously, it was like a single number. Now it's a vector of 10 values. Now, what linear algebra allows us to do is to perform this matrix multiplication operation, which we already saw, or it's also a dot product, right? Which we'll do is then when we use this operator, and we actually use it in our code here, right? We saw that we can use this notation or x dot function. If we use it in PyTorch, it will perform the dot product with each individual column of the weight matrix, and it will give us 10 answers, right? So if I perform this operation, I'm taking an input 784 elements vector, and I take this weight matrix, which is this matrix, plus the 10 elements of bias, I will get 10 results. So first result is the prediction of the 0 column. Second result is the prediction of the 1 column. Like each of these numbers is essentially our prediction for each of the digits. Like our model says, if I'm trying to find like which is the maximum here, so this is the highest number, so probably our model predicts that this is digit 1, because this would be 0, right? We are 0 based in 0 indexed, so this would be a prediction for digit 0, this is prediction for the digit 1, and so forth. And this is the highest number, so probably our model predicts that whatever we put in the input is the digit 1. So again, I just want to reiterate a little bit about this matrix multiplication operation. I messed up here a little bit with the image. It should have five elements in the input. So that what the dot product does, what this operation does, is that it takes this element multiplied by this one, then this element multiplied by this one, then this element multiplied by this one by this one, and then sum of all of them together. We get one number, we add the corresponding bias term, and we put it in our result vector as the first element. Then we do the same for the second column, and put it in this in the second element. So that will give us all 10 results. And as you can see, those computations can also be independent. So like computing a dot product between this vector and this column is independent from computing this vector and this column. So each of these results can be done independently, which GPUs are very good at doing it at a high parallelism. So all 10 of those can be computed in very quickly. Now, one thing that we did before, where we said for label 3, we need a new label. Whether it's a positive example or negative example, right? So I need to do something similar, and this trick is called one-hot vector. So one-hot vector is a special encoding where I create a vector of all zeros except from a single one in a vector that corresponds to the number in the input. So if my label was a 0, I want to put the 1 in that says this is a positive example for my classifier in position 1, right? For this column. And I want it to be a negative example for all of those. And similarly, if it's a digit 3, right? We're recognizing digit 3, so I want it to be 0, 1, 2, 3. So I want the 1 in this position, which means that it's a positive example for classifier for the column is sitting in the column 3, and it's a negative example for all other classifiers that I have in my model, because again each column here is a separate classifier essentially. So if I do this one hot vector, I can come up with a nice loss function for each, so that we can train this model. And previously we saw this sigmoid function, right? If I scroll back, the sigmoid function helped us convert any number into something between 0 and 1. So if it's a large negative number, it becomes a 0, and if it's a large positive number, it becomes a 1. And it worked fine for the case where we only try to classify positive versus negative examples. It doesn't work as well for multi-class, like here, because we have 10 digits. Why doesn't it work as well? So let's say I take this input vector, this output vector that we had before, right? I know from looking at this vector that 7 has the highest value. The second highest value is this one, 6.1, and the third highest value is this one. But if I run a sigmoid function on it, I will get 1.0 in this position, very high number in this position, and also 1.0 in this position. So because sigmoid runs this independently, and it says like all large numbers, they simply become ones or very close to ones. Now I cannot tell, like, okay, what does my model predict? Does it predict digit 1 or it predicts digit 7? Right? It says 1 in both positions. So instead we need a different function. And a very common function that people use is called softmax. Now softmax has this formula. It has a Greek letter, so I don't love to show it on my slides. I want to use the least amount of math as possible. But the idea is very simple. Let's break it down. We take our input vector. This is our input vector, and we exponentiate every single element here. So we do e to the power of the value, right? So e to this power, e to this power, e to this power. We will get 10 numbers, e to the power of this number, right? Now, why exponentiation is useful? Because it makes all numbers positive, and the bigger the number is, the bigger the exponentiated value gonna be. So after we exponentiated all of those, this will still be the largest value in the exponentiated vector. And since this was the smallest value, also after exponentiation, this will stay the smallest one. And this will be the second smallest. So it preserves this ordering, and all numbers are positive. And then now I want to get the result. So after I exponentiated them, I simply divide them by the sum of all of these numbers, so that I get something that looks like probability. So after I did this, my vector will turn into something like this. It says like there is 66% chance that it's digit 1, 24% chance that it is digit 7, 10% chance that it is digit 3, and pretty much 0 chance that it's any other digits, because those other numbers were very small, like negative numbers. So this is very good, because I really want to be like numbers between 0 and 1, and I want them to look like probability. So this is what softmax function does, and it's very commonly used in machine learning. Another benefit of using softmax is that, we need to compute derivatives to get the gradients, and ML people really like to do exponentiation, because a derivative of an exponent is the exponent itself. So derivates relatively easily. Also exponents, like the opposite of exponentiation is logarithm, and logarithms have this nice property of logarithm of two numbers multiplied by each other is just the sum of individual logarithms of these numbers. So this property is often used in machine learning, where we want to avoid the expensive multiplication operation and use a summation instead. So we very commonly use this softmax. now we need also the loss function, because it's now now we have like 10 values instead of a single value, so loss function is different from what we did before. So previously we had what is called mean square error. We took label minus prediction and squared it. It's less common to do that in a multi-class case. Instead, we use something that is called cross-entropy loss. It's also not very complex function, but I didn't want to put it here on the slide because it requires some additional math, and but it's very easy to look it up on Wikipedia or in source code in PyTorch. It's not that complex. So if we use this cross entropy loss, we can now train our model. Like, it's a very simple model, essentially like a simple matrix multiplication by a simple matrix. And we can get up to 90% accuracy on the held out dataset. It's a very nice, that such a simple model already achieves like quite good results. Now, to speed up training, we can also batch our training examples just like we saw before. Our input, if we batch our training examples, so now instead of inputting a vector and multiplying it by a matrix, we actually stack our input vectors one on top of another into a matrix, which makes batch size rows. Let's say our batch size is 50 or something. So there will be 50 rows in our batch, 784 elements, columns in our training samples, and that will be multiplied by the weight matrix. So as you can see, it's still the same operator in the PyTorch to do all of that, right? We created the W, which is the weight matrix, which we randomly initialized, 784 rows, 10 columns for each of the digits. We created the bias vector. We initialized it to zeros, again, one for each digit that we want to recognize. And we put this compute function, which is still exactly the same, dot product operator. Like it's a matrix multiply in this case, because the shape of the X is batch size by 784, and the W, its size is 784 by 10. And the result will be a vector of 10 numbers. Now, I wanted to visualize a little bit more what this operator does for people who are not familiar with linear algebra. Again, let's say I created batch, like let's say I only have, like, instead of 784 in this example, we only have five features in our model instead of 784. And I stacked 4 things together, so my batch size is 4 inputs. Now, and I'm only trying to recognize 3 digits instead of 10 digits, right? This is to make the picture smaller. So what will happen here is that each of these inputs, in each of these training samples will be multiplied by each of the columns here, and this will create the output matrix is such that this input training sample gets multiplied by this column, and the output is written in this in this cell. Then this same training sample is multiplied by the second column, and the output is written into the second output. Then again, the whole input is multiplied by the third column, and the output is written here. And then we repeat it for the second input. Again, we get 3 outputs. Then this third input, and we get 3 outputs. So this is actually, like, to produce this output, we're performing lots and lots of multiplication and summation operations here. But the GPUs are very good at running this all in parallel. Again, GPUs can do lots and lots of similar operations in parallel. They have lots of computational cores. That's why we want to batch things together. That's why we want to stack those things together instead of computing individual classifiers just for each digit. And the final loss is the mean or a sum. We can use mean function or sum function of all losses in the batch. So essentially, we will compute loss for each of the training samples, and then we sum them together, and that will be our final loss, from which we'll compute gradients. Okay, I hope this is useful so far, and we'll see you in the next session.